Hey tribe, welcome back! From the earliest days of civilization, rotation has played a crucial role in mechanical progress. Ancient humans observed the efficiency of rotational movement in nature, the steady turning of celestial bodies, the cycles of seasons, and the whirl of water currents carving landscapes. These observations led to the deliberate engineering of rotational power systems, where movement could be harnessed to accomplish labor-intensive tasks with minimal exertion. One of the first applications of rotation was in agriculture, where farmers relied on animal-driven plows to till soil efficiently. Oxen and horses, yoked to massive wooden beams, pulled these primitive plows with great force, allowing early agricultural societies to cultivate crops with significantly less manual labor. This technique evolved into more advanced rotational mechanisms, including water wheels, millstones, and pulley systems, each contributing to industry and infrastructure. The application of animal-driven rotation wasn't limited to farming. In medieval Europe and ancient African societies, animals powered grain mills, where massive stones were rotated against each other to grind grain into flour. Similarly, sugarcane crushers operated on rotational force, pressing juice from sugarcane stalks with surprising efficiency. These simple yet effective mechanisms became the foundation for mechanical engineering, shaping the way societies designed tools and machines to maximize effort. Beyond agriculture and milling, rotation became essential in transportation systems, where carts and wagons used wheels to reduce the burden of carrying goods. While wheel technology seems obvious today, it was a revolutionary breakthrough in ancient times, enabling the movement of heavy materials over long distances. As civilizations expanded, the ability to transport stone, food, and goods across vast territories accelerated cultural and economic exchanges, fueling progress in ways unimaginable before rotational power entered the equation. While rotation helped civilizations move materials efficiently, leverage enabled them to lift, transport, and shape massive structures that seemed impossible by human strength alone. The principles of leverage were understood in ancient Africa, Egypt, and Mesopotamia, where engineers used wooden beams, pulleys, and ramps to construct enduring monuments. Leverage was used extensively in Egyptian pyramid building, where long wooden beams acted as counterweights, allowing massive limestone blocks to be moved with precision. This simple yet powerful technique depended on the principle of force amplification, applying a small force over a long distance to achieve a greater force output. Workers using fulcrums and levers could shift multi-ton stones with minimal effort, leading to construction efficiency that remains an architectural marvel. In Greek and Roman engineering, compound pulley systems enhanced leverage techniques. These pulleys allowed workers to hoist enormous stone blocks for temple columns, aqueducts, and fortifications. Ancient cities benefited from these innovations, as leverage-based scaffolding became a key feature in construction, military defenses, and irrigation systems. One of the lesser-known leverage techniques was water-based lifting, where civilizations used buoyancy and floating platforms to transport massive stone slabs. Ancient African builders may have employed submerged logs tied to stones, reducing their weight in water for easier transportation. Similar hydraulic concepts are used today in modern shipbuilding and dam construction. The oldest evidence of mining in Africa dates back 43,000 years to Ngwenya Mine in Eswatini, one of the most significant prehistoric mining sites in the world. Early humans extracted red ochre pigments, using them for body decoration, rock paintings, and burial rituals. This ancient mining culture showcased humanity's first understanding of natural resources and their utility in both spiritual and practical applications. By the Iron Age, African civilizations transitioned from ochre extraction to iron smelting, developing early metallurgy techniques that would later influence global industry. The arrival of Bantu-speaking technologists brought advanced ironworking technologies to regions like Nigeria, Sudan, and Mali, leading to the mass production of tools, weapons, and trade goods. West Africa, particularly sites in Burkina Faso and Nigeria, was home to advanced clay furnaces designed for iron smelting. These furnaces operated on high-temperature combustion, allowing the extraction and refinement of iron ore into usable metals. The Kingdom of Meroe in Sudan had one of the most sophisticated iron-producing centers, where enormous slag deposits revealed evidence of large-scale ironworking operations. Ancient African metallurgists did not simply extract and refine metals. They developed casting techniques that allowed them to shape raw materials into precise forms. Using clay molds and lost wax casting, artisans created decorative bronze plaques, weaponry, and religious artifacts. The Nok civilization in Nigeria, dating back to 1500 BCE, was among the earliest to refine terracotta and metal casting techniques, producing realistic sculptures and practical tools. The Benin Kingdom, renowned for its bronze artistry, perfected lost wax casting, allowing sculptors to create intricate designs with high precision. These casting techniques ensured that metal could be repurposed, reshaped, and efficiently distributed across trade routes. Beyond metallurgy, clay furnaces played an essential role in pottery production and ceramic firing, enabling civilizations to construct durable cooking vessels, storage containers, and architectural tiles. Pottery kilns were widespread across Africa, from Saharan desert communities to coastal trading cities. Many ancient African builders developed natural concrete-like mixtures, relying on clay lime ash and crushed stone to reinforce structures. The Great Mosque of Djenné in Mali, constructed in the 13th century, used mud brick reinforced with natural binders, demonstrating methods similar to early concrete formation. Egyptians were among the first to mix lime-based mortar, creating strong binding materials for pyramid construction. Meanwhile, Nubian architects used clay and stone aggregates to strengthen fortifications along the Nile River. One particularly intriguing hypothesis is the Schiltz disk theory, which suggests that ancient African builders may have used rotary mixing systems similar to those found in modern cement trucks. If builders employed rotating stone disks to mix aggregates and water, they could have achieved uniform blends of concrete-like substances long before industrial cement technology emerged. While direct evidence of ancient concrete mixing systems remains scarce, the principles found in grain mills, pottery wheels, and rotary furnaces suggest that early civilizations understood uniform material blending, a key aspect of modern concrete production. From rotational power and leverage to mining, metallurgy, casting, and concrete mixing, ancient African innovations paved the way for modern engineering. These civilizations mastered techniques that allowed them to build enduring structures, refine metals, and harness mechanical principles in ways that continue to inspire modern construction and manufacturing. Today, researchers are revisiting sustainable methods used by ancient African builders, studying natural clay mixtures and indigenous metalworking traditions to develop eco-friendly alternatives to cement and industrial smelting. By combining the wisdom of past civilizations with modern technology, humanity can rediscover lost engineering principles that offer sustainable solutions for future infrastructure. As new discoveries emerge, Africa's role in early mechanical and architectural advancements will continue to reshape historical narratives, highlighting the continent's deep contributions to global innovation. This brings together all the interconnected knowledge we explored, weaving it into a historical technological journey that flows from rotational power to metallurgy and ancient concrete techniques. Don't forget to smash that like button. Do it for the algorithm. Subscribe to join the tribe. And share this with a friend if they might find it as interesting as you did. Welcome to the tribe. Glad to have you in our family, LaViand Media.